Hello everyone, in this session we will cover our good friend sulfur for oxide, SO2, which is present in sulfur in its compound. So isolating SO2, let's look at how it's prepared and some few physical and chemical properties and its uses. Without further ado, let's dive straight into it. How is sulfur for oxide produced or manufactured? There are two ways of producing SO2. The first way is reacting copper turnings with hot concentrated sulfuric 6 acid. Okay, and the second, we will discuss the second way later, but we start with the first one. Copper turnings with hot concentrated sulfuric 6 acid. So the overall equation for the reaction will be copper turnings will react with the sulfuric 6 acid, the concentrated sulfuric 6 acid, to form copper 2 sulfate, sulfur oxide gas, and water. So this is the setup that is used. Now, as it is a crystal funnel dipped into the concentrated sulfuric 6 acid flowing into the round bottom flask, and we have copper turnings and we have heat here, right? We can see into the next flat bottom flask we have concentrated sulfuric 6 acid. What is the use of conc H2SO4? It is to dry the gas. You can go from the round bottom flask directly to the collecting flask without this without the use of conc H2SO4, but that gas will be wet, it won't be dry. To dry the gas you use concentrated H2SO4. Why don't you use calcium oxide? Because calcium oxide is the base and sulfur oxide is an acidic gas. So the two will react, and neither anhydrous calcium chloride is used because it forms a complex salt. So this is the overall equation for the reaction: copper plus conc H2SO4. Conc H2SO4 is 98% H2SO4 and it is a liquid, to form copper 2 sulfate aqueous SO2 gas plus water. Now, what are the few physical properties of sulfur oxide? The first one is it is a colorless gas. Unlike nitrogen oxide, which is a brown gas, SO2 is a colorless gas. Yes, it is. It has a pungent choking smell. It is not odorless. It can choke someone and it is poisonous. SO2 is an acidic gas. Okay. It can turn moist blue litmus paper to red, right? Then SO2 is collected by downward delivery. Which method of gas collection is this? Downward delivery, downward delivery, also called upward displacement of air. So that means that SO2 is denser than air. Now to note, SO2 is almost twice as dense than air. It is highly soluble in water. SO2 is highly soluble in water to form an acidic solution. Now we go to the solution that it forms. It is an acidic gas, dissolves in water to form sulfuric 4 acid. It doesn't form sulfuric 6 acid. It forms sulfuric 4 acid. Sulfuric 4 acid is written as H2SO3. Now this H2SO3 is not just there. It has some special characteristic. It is used as a bleaching agent. In H2SO3, the sulfite in H2SO3 are ions that are used for bleaching. Now, a very important question that can be asked is, what happens when moist blue litmus paper is placed in a gas jar containing SO2? Now, the observation will be the moist blue litmus paper changes from blue to red and then white. Why? Let's repeat. From blue to red and then white. This is because, first of all, you have a gas jar, right? It has SO2 inside. You put a moist blue litmus paper in. It will first change to red. Why? Because SO2 is an acidic gas. Acidic gas. Okay? Then it will be bleached. Why? Because that SO2 and the moisture that the litmus paper has will form a compound of sulfuric 4 acid. Sulfuric 4 acid having the sulfite ions which are bleaching. So the sulfite ions in H2SO3 bleach the litmus paper to white. So H2SO3 has a bleaching property. It can also bleach flower petals from pink to white. It bleaches by reduction. Now what is bleaching? Bleaching is the whitening of a naturally colored substance by either oxidation or reduction, right? Whitening of a natural colored substance by either oxidation or reduction. Now SO2 bleaches by reduction. It removes the oxygen from the element that is bleached. Let's say flower petals are being bleached, flower petals, but in our example here we have used dye. How it bleaches by reduction is it removes the atomic oxygen from the dye or from the flower petals. That causes it to lose its naturally coloring, its natural coloring pigment. So H2SO3 reacts with dye. Now the dye loses its oxygen, dye minus O plus the oxygen that is lost by the dye goes and adds up here plus oxygen. So this was O3 plus O to form O4. So H2SO4. We repeat, sulfuric 4 acid will bleach dye by reduction. It bleaches dye by reduction to form dye less oxygen. The atomic oxygen from dye is removed. The atomic oxygen that is lost, where does it go? It doesn't disappear into the air, no. It goes into the H2SO3, adds itself to the 3 oxygens that are already there to form H2SO4. Now the difference between bleaching agent bleaching property of sulfur 4 oxide SO2 and the bleaching action of chlorine, there are 2 differences. Chlorine is also a bleaching agent, but SO2, the bleaching action of SO2 is temporary. Okay, it's temporary, and the bleaching action of chlorine is permanent. So that's one difference, permanent, and this is temporary. Okay, the second action is chlorine bleaches by oxidation. And SO2 bleaches by reduction. So if chlorine were here instead of SO2 or SO3 to negative, instead of sulfite ions, the dye would gain the oxygen and it will be oxidized. It would be dye plus O to form permanent bleaching. Now before we go into the reduction and oxidation further properties, let's look at the uses of sulfur 4 oxide. Now the main and the most important use is it is used in the manufacture of sulfuric 6 acid. That's the most important one, you have to have it on your fingertips. Another one is manufacture of bleaching agents, used as a disinfectant and a solvent for glue. You just need to know them the way they are. Now, what is the test for sulfur 4 oxide gas? You bubble sulfur 4 oxide through a solution. There are 2 solutions you can use. Through either a solution of potassium manganate 7 or a solution of potassium dichromate 6. Potassium manganate 7 written as KMnO4 or potassium dichromate 6 written as K2Cr2O7. What is the color change? How do you confirm presence of SO2? If potassium manganate 7 is used, the solution changes color. What color is potassium manganate 7? Of course it's purple. So when SO2 is bubbled through it, it changes from purple to colorless. Okay? And when it is bubbled through potassium dichromate 6, the color changes orange to green. Orange to green. So for you to confirm presence of SO2 by bubbling it through potassium dichromate 6, the color has to change from orange to green. Let's recess. We forgot to mention gas X. What is gas X? Gas X is quick gas. is sulfur oxide. Because the copper tannins are reacting with sulfuric 6 acid to form copper 2 sulfate, which is formed in the round bottom flask only. The H2SO4 concentrated dries the gas and you collect dry sulfur oxide in this collecting flask. So our second method of preparation involves either a sodium or potassium sulfite plus either dilute hydrochloric acid or dilute sulfuric 6 acid. So you can use either of the two but not both of them together. Okay, so in one reaction, let's say you can use sodium sulfite plus dilute hydrochloric acid, or sodium sulfite plus dilute sulfuric 6 acid, or potassium sulfite plus dilute hydrochloric acid, or potassium sulfite plus dilute sulfuric 6 acid. So these are your options. Now the example that we have taken here, we have taken two examples. Either sodium sulfite plus dilute HCl to give you sodium chloride plus sulfur oxide plus water, or potassium sulfite plus dilute H2SO4 plus, to form potassium sulfate plus SO2G plus water. Now the setup, as you can see, is the same. Is the same as in the first reproduction. The only thing that's changing is the reactants here. Sodium or potassium sulfite found in the round bottom flask, and comes in dilute HCl. Now dilute HCl or the H2SO4. Concentrated H2SO4 found in the flat bottom flask. Of course, we know what's the use of that: to dry the gas. What's the gas? X, collected by downward delivery. Because it is denser than air, it is dry, SO2. Okay, so that's the second method of preparation. Now we go to the reducing activity of sulfur oxide. Now, as we mentioned here previously, sulfur oxide, the test for the gas is it causes potassium manganate 7 to change from purple to colorless, or changes potassium dichromate 6 from orange to green. Now, why is the color change that we are seeing? What is the reason behind it? This is because of reduction of ions, leading to reduction of oxidation numbers. So why is the potassium manganate 7 changing from purple to colorless? Because the potassium manganate 7, the reduction of potassium manganate 7 reduces manganate 7 ions. So the purple color is because of the manganate 7 ions. And the colorless color of the solution that is changed from purple is because of the manganese 2 ions. So potassium manganate 7, when SO2 is bubbled through it, it changes from purple to colorless. Why? Because SO2 reduces manganate 7 ions, which are purple, to manganese 4 ions, to manganese 2 ions, which are colorless. Now the same applies for potassium dichromate 6. Why does it change from orange to green? The orange color, what is responsible for the orange color? Dichromate 6 ions. And what is responsible for the green color? Chromium 3 ions. So for the color change to occur, the dichromate 6 ions are changing to chromium 3 ions. Dichromate 6 ions were originally orange, but the chromium 3 ions are green. That is why the color changed. So the dichromate 6 ions oxidation number positive 6 is changing to chromium 3 ions oxidation number positive 3. So this is reduction, isn't it? Decrease in oxidation number. Now it also reduces ion 3 ions, which are brown in color, to ion 2 ions, which are green in color. So oxidation number of ion in ion 3 is 3 positive, and in ion 2 it's 2 positive. So the oxidation number is going down. That's why SO2 is reducing ion 3 ions to ion 2 ions. That is why the color changes from brown to green. The last part, it decolorizes bromine water from yellow to colorless. Bromine water is yellow because of what? Because of the chloric 1 acid, the hypobromous acid. So the hypobromous acid is HOBr, changes to HBr. So when the oxygen is lost, it leads to reduction. Now, the oxidation property of sulfur 4 oxide is that when it is reacted with hydrogen sulfide gas, there are two gases when they are reacted, SO2 and hydrogen sulfide. When hydrogen sulfide is reacted with SO2, with sulfur 4 oxide, what is the observation? The observation is a yellow solid and a colorless liquid. Think of that, a yellow solid and a colorless liquid. Why? Because SO2 will oxidize hydrogen sulfide to form sulfur. Okay? So SO2 will oxidize hydrogen sulfide to form sulfur. Isn't it? The hydrogens will be removed and itself will be reduced to sulfur and water. So sulfur being yellow is the reason for the yellow solid, and the colorless liquid is because of the water. So if they bring for you a setup in which SO2 is reacting with hydrogen sulfide, the observation is a yellow solid and a colorless liquid are deposited. Why? Because sulfur 4 oxide oxidizes hydrogen sulfide to form sulfur, while itself is reduced. The oxygens are removed. They are removed to also form sulfur, and water is formed as a byproduct. That's why the colorless liquid is formed. I think we are clear there. We can repeat one more time. H2S is oxidized to form sulfur. SO2 reduces itself to form, is reduced by H2S to form sulfur. Both of them are forming sulfur. However, the oxygens of SO2 are removed, so it is reduced, while the hydrogens of H2S are removed, so it is oxidized. That is why forming a yellow solid, which is sulfur, and a colorless liquid, which is water. Now, we have seen magnesium burning with NO2, with N2O, with nitrogen 2 oxide. It also burns with sulfur 4 oxide. It reacts with sulfur 4 oxide, not burns, it reacts with sulfur 4 oxide. How does it react with sulfur 4 oxide? The reaction of burning magnesium is highly exothermic. So it breaks down the sulfur 4 oxide into sulfur and oxygen. The magnesium breaks down sulfur 4 oxide into sulfur and oxygen. The magnesium then combines with oxygen, which supports combustion, to form magnesium oxide. What's the observation? A white solid and burns with a bright white flame. We already covered that in nitrogen 4 oxide. Bright white flame and a yellow solid of sulfur. So what is the observation here? Mixture of a white and yellow solid. Why? We are not going to write this, but the explanation I'm giving is what you can write exactly in exam. The reaction of burning magnesium is highly exothermic. It breaks down sulfur 4 oxide into sulfur and oxygen. Oxygen, since it supports combustion, it combines with magnesium to form magnesium oxide, and the sulfur is given as a byproduct. So magnesium oxide being yellow, being white, and sulfur being yellow, that's why the mixture of white and yellow. This is the question. Observation: white and yellow solid mixture deposited. Why? We just give the answer. Now, our last part in the sulfur 4 oxide is reaction with alkali. Alkali, we said sodium hydroxide, potassium hydroxide. So sodium hydroxide will react with sulfur 4 oxide to form sodium sulfite and water. As we know, sodium hydroxide base, sulfur 4 oxide acid, to form sodium sulfite, which is a neutral salt, plus water. As we know, acid reacts with base to form salt and water. So it's a neutral salt and water. However, when you bubble excess sulfur 4 oxide through the sodium sulfite, when the sodium sulfite, you take it and you bubble excess sulfur 4 oxide together with the water, you form sodium hydrogen sulfate, which is soluble. So I think that's it for sulfur 4 oxide. Feel free to ask any questions. Like, subscribe, share. Thank you so much for watching. Stay tuned.